Assalamualaikum. This is your Thermodynamics 2 class. Okay, so for the Friday lecture. So if anyone confirm that what appears on my screen right now, lecture number 6. Can anyone confirm to me?
Yes, sir. Sir, lecture 6, chapter 10.
Okay, thank you
Is
so
visible
much.
on your
Okay, so coming towards the lecture number 6. Okay, so it is again from your chapter number 10. Okay, so previously we already talked about the vapor power cycle, but specifically using our open feed water heater, okay, in order to increase the efficiency of our cycle. So again today lecture is also regarding to regenerative Rankine cycle. So we already talk about the regenerative Rankine cycle, what are their advantages and why we have to use the regenerative Rankine cycles in order to achieve maximum efficiency. So just quickly we can go through it that why we need a regenerative Rankine cycle. So if we just consider a TS diagram for our Rankine cycle, so it is a vapor dome. Okay, so we will start with the, for example, point number 3, which is your turbine, and then it is a straight line because it is an isentropic process from your in the turbine, isentropic expansion, and then from 4 to 1 there will be a pump. Okay, so here will be a pump where we have to install condenser where there will be a heat rejection over there. Okay, and then from 1 to 2 there will be one pump, which is an isentropic compression process. Okay, so coming towards the heat addition process, so heat addition is between 2 to 3. So we have to, and it is in the constant pressure one. Okay, so we have to just draw a constant pressure line, and we have to draw like this. Okay, so this 2 and 3 is considered as a uh, heat addition process, Q in. Okay, and sure. Okay, okay, so this is your Rankine cycle. So what happened with your Rankine cycle is previously whenever we talk about is that this 2 and 2 dash, which is shown in your diagram, are at relatively low temperature. Okay, so if it is at low temperature, so this lowers the average heat addition temperature and thus cycle efficiency. So the idea behind the regenerative Rankine cycle is to increase this point to either on that side, or you can increase as much as you can. Okay, so that your thermal stresses in your boiler will be less and you will get the maximum efficiency. Also the area under the curve also improve. Okay, so now we already talk about the open feed water heater. So open feed water heater also we increase this point number 2, the temperature of this 2, and in closed feed water also we have to increase this temperature of point 2. Okay, so the main difference behind these two are, so we already see that a feed water heater is basically a heat exchanger. Okay, so in which we have to just exchange the heat transfer from the steam to the feed water. Okay, and feed water that is coming from your pump, and either by mixing the two fluid stream. Okay, so whenever we are talking about mixing of two stream, because when we saw the open feed water heater, we said we saw that there are two streams that are coming and mix in the heat exchanger, but in the closed feed water heater there is no mixing. Okay, so this is the basic difference between these two, that in the open feed water heater the fluids mix together, but in the closed feed water heater there is no mixing of the fluids, but still there will be a heat exchange. Okay, so we will see that how we can exchange heat without any mixing of these two fluid stream. Okay, so just the open and closed feed water heater can be compared as follow. Open feed water heater are simple and inexpensive and have a good heat transfer characteristic. Okay, so positive thing about open feed water heater, and they also bring the feed water to the saturation state for each heater. However, a pump is required to handle the feed water. So this is a negative point about the open feed water heater. So that if we install number of feed water heaters in your vapor power cycle, so it's mean we need uh, a separate pump for each feed water heater. So in this way, the cost is also affected because we have to require more pumps also. And the closed feed water heater are more complex because of the internal tubing network, and thus they are more expensive also. Okay, so the closed feed water is also a complex system because the internal tubing, because there's heat exchanger in which there was internal tubing network, so that's why it become more expensive also. And the heat transfer is in a closed feed water heater is also less effective since the two streams are not allowed to be in direct contact. Okay, so it is also heat transfer less effective in the closed feed water heater. But the positive thing about the closed feed water heater is that closed feed water heater do not require separate pump for each heater. For example, if we install number of feed water heater, closed feed water heater, so that we do not need extra pump in order to pump the fluid. Okay, so we will also see that how this will happen. Okay, so but the major differences in the open and closed feed water is just these two, that in one there will be more pumps are required, and in the second one in the closed feed water heater there are less pumps are required for each heater, but it will not significantly improve the efficiency by just adding the closed feed water heater. So now the question is that why we have to study the closed feed water heater if it is not increasing the efficiency significantly. So the main thing is that whenever we are talking about vapor power cycle, we have to use combination of open and closed feed water heater. Okay, and as per requirement of your design of your power plant also. Okay, for example, if we need that the cost is an important factor, so that we have to just compensate that how many open feed water and closed feed water heater we have to use in our city power plants. Okay, so this is the major difference between it. So we will also see the thermodynamically how to thermodynamically analyze this closed feed water heater. So just looking towards the schematic diagram of your feed water heater, both of the feed water heaters. So this is your open feed water heater, which is shown over there, and this is your closed feed water heater. So as we already talked about the open feed water heater, there is again boiler is there, open feed water heater, boiler is also there at the closed feed water heater. Turbine is here, turbine is also in the closed feed water heater. So now the difference is that condenser is also there, condenser is also there, and there's two pumps also. Okay, right now there's two pumps are showing over there because each of them are the single feed water heater system. But if there are multiple feed water system, then in the open feed water heater you require multiple pumps. But in the closed feed water heater, you can use a single pump to just inject the stream of fluid through all the closed feed water heater. So this is the major difference. Okay, so now coming towards your open feed water heater. So if you can see that whenever we are talking about open feed water heater, the steam number 6 and steam number 2 come to the open feed water heater chamber and just mix together and just uh, exit from the point number 3. Okay, so there is a mixing over there. Okay, so these two streams mix together. But when we are talking about the closed feed water heater, okay, so if you can see that the point number 2, okay, so that is going towards your point number, this is your heat exchanger basically. Okay, so the same flow, for example, if the flow is 1 minus y at point number 2, so 1 minus y flow is again at point number 9. Okay, so there is no mixing over there. So it's come in and it's exchange the heat and it just exit. Okay, on the same mass fraction. Okay, so similar for this one. So this is y, for example. So it goes from 7 to 3. Okay, without change in fraction. Okay, so same y is there, same y is there, and it's just exchange the heat and exit from your heat exchanger. Okay, so there is no mixing over there. Okay, but we have to mix it together in a separate mixing chamber. Okay, so the reason behind is, so the main difference is that previously we just talk about that these P6, P3 and P2 all are same. Okay, in order to make the our cycle by working on a right direction. But here we do not need to make these pressures equal, so that P7 is not equal to these pressure P2 or any other pressure. Okay, so that we can operate this cycle on different pressures also. Okay, for example, if your design criteria for designing the steam power plant is that you have to maintain different pressures, so then you have to use closed feed water heater rather than the open feed water heater. But if you have the requirement that you have to make both the pressure limits also, the pressure is same also, and your in the one part the pressure is different also, so then you have to use the combination of closed feed water and open feed water heater in your steam power plant. Okay, so now coming towards the TS diagram of this cycle. Okay, so in mixing chamber we will talk about later that how these mix together when we are working on the TS diagram. So we will see over there also. Okay, so coming towards that, this y and this 1 minus y again comes to mixing chamber, and here your fraction will be 1. Okay, so that we will get the 1 fraction over there. So again the bleeded portion is extracted from 7, sum of portion will goes toward 8. So similar uh, mechanism which we already discussed in the open feed water heater. So in the 6 there will be a bleeded steam, in the 7 the remaining portion will go towards. Okay, so coming towards the TS diagram for this, I will try to build over there so that you can easily understand that how to build the TS diagram for both of the cycles. Okay, so coming towards the TS diagram, you can just start from, so this is TS. So I will just compare these two diagrams with the closed feed water heater and open feed water heater. Right now I am drawing the open feed water heater. So you have to draw the vapor dome. Okay, so point number 5, this is your point number 5. You already know that it will be in the superheated region. Okay, so you just draw from, either you can start from number 5 or you can start from your pump point also, because you know the state of these. Okay, so point number 5 is on your superheated region. So coming toward point number 6, we do not know the state of this point. Okay, so we have to judge it from your problem statement also, at where this point 6 lies. Either it will be inside the dome or either it will be outside the dome. Right now I am just trying to draw the in the outside of the dome. Okay, so now point number 7, we already know that this is in the two-phase region. Okay, so because it is going to the condenser, and this point number 5, 6 and number 7 will join together because there is the expansion and it is an isentropic expansion. Okay, so that's why these lines are joined together in the open feed water heater. Okay, so now coming towards that, there was bleeded steam. So bleeded steam will be extracted at point number 6. Okay, so here we have to just extract bleeded steam, and some of your portion will goes towards your condenser part. Okay, so it will goes toward your condenser part also. Now after condenser there will be a pump where there will be isentropic expansion, so it will be a straight line like this. Okay, and then we already talk about that the P6, P2 and P3 are equal in your closed feed water heater. So this line, which is your point number 3, because here there will be a mixing, so this is at constant pressure. Okay, so this line will be drawn like this. So now coming towards point number 3, so point number 3 there will be a gain pump. Okay, so in order to increase the temperature of your working fluid also. Okay, so it is also isentropic expansion compression process, isentropic compression process, and then it is also on the constant pressure. The P4 is equal to P5. Okay, so then you have to draw your line like this. Okay, so this is the and this is 1 minus y, which is going towards you this one. Okay, so now coming towards your closed feed water heater. So closed feed water heater, you also have to draw the TS diagram. Okay, again you have to draw the vapor dome. Okay, so now again your point number 6 is known to you. So this is your superheated one. So superheated point number 6, point number 7, either it will be outside the dome, either it will be inside the dome. We will judge from your problem statement. Point number 8, so this is point number 7 now, and point number 8, it is inside the dome because it is going towards condenser, it is in the two-phase region. Okay, so again there will be a isentropic expansion from 6 to 8, and there will be a bleeded steam which is extracted at point number 7. You can just notice from your schematic diagram also. Okay, so point number 7, we have to extract some bleeded steam, and point number 8, rest of the portion will go towards your point number 8. Okay, so from 1 to 2 there will be a isentropic compression process. So 1 and number 2. Okay, so now coming towards the main thing, that how we can draw these 9, 5 and 4 points. Okay, so as we noticed that whenever this 2, which is here, exchange the heat inside this heat exchanger number 9. Okay, so it's mean that the temperature of this T2 will be less than T9. Okay, so because T9 will be greater. Okay, so temperature of 9 will be greater. So when there it will be greater, and the pressure of P2, because there will be no mixing over there, so the pressure of 2 is equal to P9. Okay, because it is the same pressure line. Okay, and P7 is equal to P3. Okay, so now if it is on the same pressure line, it's mean that your so this is the pressure line. Wait a second, I will try to. Okay, so point number 9, you can just mention over there that it will be. Okay, another important point is that this point number 2 will not be joined over there. This will be on a because this pressure, your P2, P9, P5, okay, because these are all on the same pressure, and P6, these all are on the same pressure. So we have to just join over there. Okay, so this point join over there. Okay, so because these are all on the same pressure. So this is point number 2. Okay, so now coming towards your point number 9. Okay, so point number 9, when you mix together, so this point number 9 will be at higher temperature, so we can just mark it that this is point number 9. Okay, for example, just we have to, and this point will not be above from this line. Okay, because if these because if you can notice that the steam is coming over there. Okay, and that will be at the highest temperature. Okay, and the temperature of this point number 9 will cannot be above this point number 7. Okay, so that's why we have to make this point number 9 equal to point number 7 or below the point number 7, below the point number 7. Okay, so that's why you have to just make sure that this point number 9 is in between these one. And we will figure out that the exact value by using the problem statement. Okay, so now coming towards your point number 3. So point number 3, again there will be isentropic compression. So that will be isentropic compression process. I'm trying to make it clear, but due to some issues I have not clear. Okay, 1 minus y coming over there, y is coming over there. Okay, so now 2, 9, 4 we already drawn. Now the one point which is left is number 5. Okay, so where the point 5 is. Okay, so point 5 is if you see that point number 9, it is at the T9. For example, it is on some temperature, and T4 is on other temperature. We can just mention it's T4, and the temperature of your T5 cannot be greater than T4. Okay, so because it is a superheated steam. Okay, so it will not be greater than T4, so that we have to make it less than T4, and it is in between point number 9 and point number 4, because the temperature will be in when there will be a mixing chamber, so there will be, it comes to be on some location over there. Okay, so this is how you can draw the T5 also. Okay, so all the points are now on our TS diagram. So this is how you can try to develop. So this is point number 3. Okay, I know it will be a tedious process because there are many points and you have to draw it by yourself. We will also look from one example so that it will make you more clear about it, that how to draw the TS diagram for your, this is your Q rejection. Okay, so this is the TS diagram for your closed feed water heater system. So now coming towards the main part of your today's session is your example. Okay, so clearly it is shown over there because I have just drawn. I will try to draw it. So this is how you can draw the TS diagram for open feed water heater, and this is for your closed feed water heater. So you have to make it clear by using the scale or okay. If you have any question, you can ask me also. Okay, now you have to just read this question first. Okay, so this is regarding your closed feed water heater. So a steam power plant operate on an ideal regenerative Rankine cycle. Steam enter the turbine at 6 megapascal and 450 degrees Celsius. So your higher pressure and temperature is given in the question. Is condensed in the condenser at 20 kilopascal. Lower pressure of the condenser is given. Steam is extracted from the turbine. So bleeded steam pressure is also given. So your point number 6 pressure is given in your question 0.4 to heat the feed water in a closed feed water heater. So this is mentioned that it is a closed feed water heater system. Assume that the feed water leaves the heater at the condensation temperature of the extracted steam, and that the extracted steam leaves the heater as a saturated liquid. Okay, and so this is an important point that it is that the extracted steam leave the heater as a saturated liquid and is pumped to the line carrying the feed water. Show the cycle on the TS diagram. So you have to build the TS diagram for this cycle and determine the network also. And determine the network output of per kilogram of the steam flowing through the boiler and thermal efficiency of the cycle also. Okay, so again you have to just see the schematic diagram that your boiler, okay, turbine, you have the bleeded steam coming towards 6. It's go from your heat exchanger, and the same mass flow will be at point number 3. At point number 2 there will be a pump, okay, so that is sending the feed water from your condenser also, and then there will be exchange of heat from your till point number 8, keeping your fraction will be constant. So it will be 1 minus y over there, it will be y, there will be y, this is 1 minus y. Okay, and in the mixing chamber there will be a mixing of these two fluid streams which are on different temperature and turn around to be number 4, and then we get the increase in T4, that is at your entry of your boiler point. Okay, so that this is main objective of our regenerative Rankine cycle. We have to increase this point number 4. Okay, so this is your problem statement. So we will start solving this statement. Okay, so starting from your TS diagram, so you have to build the TS diagram for this cycle again. Okay, so for the TS diagram, again you have to just vapor dome, you have to draw the vapor dome. Point number 5 you already know over there. Okay, so the points I think the numbering of points are different from the previous one, so you can just make sure that you have to. Okay, so point number 6 is in your outside or inside, we will judge from your question. Point number 7 is in the condenser one, so it will be, okay, so there will be isentropic expansion process from 5 to 7. Okay, so bleeded steam will go towards from here. Okay, and then again you have to make this pressure 5 equal to the pump exit temperature. So 1 2. So this is your 3, this is your number 9. Okay, so you have to correlate with your schematic diagram which we already see in the previous slide. Okay, so point number 8, which is here, and this is after your mixing. This is point number 4, and all the points are right now. So we have given with 6 megapascal pressure over there. 0.4 megapascal is given that the bleeded steam is extracted at this pressure, and your 20 kilopascal the condenser pressure is given over there. Okay, so this is your y part, which is fraction of steam going towards here, and this is 1 minus y, which is a fraction of steam going towards your condenser. Okay, so starting from your point number 1, so point number 1 pressure is given in your question. So state number 1, P1 is equal to 10 kilopascal. So you have to go to just your steam tables, your water saturated water tables, and against the pressure you have to find the value. Okay, so this is 20 kilopascal, sorry. Okay, so you have to just find the enthalpy value, and this turns out to be 251.42 kilojoule per kg. I will suggest you have to just open the thermodynamics table in front of you whenever we have to solve the question, so that you get the better understanding how we get the values. So again you have to need specific volume at 1 also, because we need to find the pump 1 work, and also we have to find the pump 2 work also. So specific volume at 1 is from your thermodynamics table 17, meter cube per kg. Okay, so you have to find pump 1 work, which is equal to specific volume at 1, P2 minus P1. Specific volume you already find. P2 is given in the question, which is 6 megapascal, and your point number 1 is also known to you, which is your P1 20 kilopascal. So just plug in all the value and you will get the 6.08 kilojoule per kg. Okay, so now coming toward your state number 2, so H2, the same procedure which we follow in the Rankine cycle. So H2 is equal to H1 plus W pump 1. Okay, so now H1 is known to you, which is 251.42, and W pump is also known to you, 6.08. So just you can add these two terms and you will get the value 257.50 kilojoule per kg. Okay, so coming to a state number 3, so state number 3 pressure is also known to us. So P3, which is equal to, okay, so we will make a look on a clear TS diagram for this one. Okay, so P3 is equal to 0.4 megapascal, and then you have to again go to your pressure tables and pressure against your pressure for your water tables, and you will get H3 value at HF saturated liquid point, which turns to be 604.66 kilojoule per kg. Okay, so again you have to find a specific volume at 3 because we need the pump 2 work also to find the pump 2 work. So again you have to go towards your saturated liquid and you can just note down the value 0.001084 meter cube per kg against your 0.4 megapascal pressure. So we have to find the pump 2 work also. So it will be specific volume at 3, your P9, so B9 and minus P3. Okay, so specific volume at 3 is given, P9 is given in your question, P3 is also given in your question. So just you have to solve it and you will get 6.07 kilojoule per kg. So coming towards your enthalpy at H9, at point number 9, so H9 is equal to H3 plus W pump 2. Okay, so now H3 is known to us, which is 604.66, plus W pump 2 is also known to you, 6.07. Okay, so you just have to add these two and you will get 610.73 kilojoule per kg. Okay, so for H9 we have just find the enthalpy. Okay, so now important point is how to find the enthalpies of H8 and H4. Okay, so in the question, if it is mentioned your specific states of these point number 8 and point number 4, okay, so then you have to find these properties from your thermodynamics table. But here if we can just notice that at point number 9 and 8, two streams are coming together and mix with each other. Okay, and these two streams have the one stream is has an enthalpy value of 610.73. Okay, so if we notice that these are all on the same pressure line. Okay, so here we have to just assume, so this is an only assumption. Okay, in reality this point number 8 enthalpy is I think significantly there will be significantly small difference between the H9 and H8 enthalpy. Okay, so we just assume that your H9 enthalpy is equal to H8 enthalpy and equal to H4 enthalpy. Okay, because this if you can find it, okay, you can easily find if the data is available. So you will notice that for example your H8, if all the data is available, so you can just notice that it will be turns out 609.99 or something like this. Okay, so the amount of difference between these two values are too small. Okay, so that why we have to put effort in order to finding the enthalpies of these points. So rather than we just assume that H9 is equal to H8 and is equal to H4. So similar for the H4 also. So H4 is also close to your 610 or something value. Okay, so that's why, so this is an important assumption over there. So you have to just make sure that you have to assume that these enthalpies are equal. Okay, so now coming towards state number 5. Okay, so state number 5. So state number 5 over there. So you already know the pressure P5 is equal to 6 megapascal, T5 is equal to 450 degrees Celsius. Okay, so this is a superheated temperature, and then you have to just H5 is equal to 3302.9 kilojoule per kg. S5 is equal to 6.7219 kilojoule per kg. Okay, so you have to just follow the stream tables, okay, and for superheated one, and you will get the value against this pressure and temperature. So now coming towards your point number 6. So point number 6, we do not know either it will be inside the dome or either it will be outside the dome when we draw the TS diagram. So you have to judge it by yourself, and we will see that how we can judge it. Okay, so state number 6, over pressure P5 is equal to 6 megapascal is given. Okay, sorry, P6 is equal to this P6 equal to 0.4 megapascal. Okay, so what you have to do is you already know that the enthalpy at 6 is equal to enthalpy at entropy of 6 is equal to entropy at 5. Okay, because it is an isentropic process. So you have to just go and check it against the 0.4 megapascal. You have to go your thermodynamics table, and you will find the value Sg, which is your entropy value at gaseous state for this pressure, and you will get that it will be 6.8955. Okay, and this Sg value is greater than your S5. Okay, and when it will be greater, it is in the two-phase region. Okay, so this is one check, you have to do it by yourself. Okay, whenever you have to judge this point number 6 or any point, whenever you have the confusion that this is in the two-phase region or either it will be in the superheated region. So Sg is less than S, it will be superheated region. Superheated. So now our check will be this one, that Sg is greater than S5 because 6.8995 is greater than 6.7219. Okay, so it's mean that we have to find the thermodynamics value for our two-phase region. Okay, so now we have to just find the x6 value because we need the quality whenever we have to judge that it will be in the two-phase region. So H6 minus SF and SFG. So you have to find the values against 0.4 megapascal, and you can just put all the value and you will get 0.9661. Okay, so again we have to find the H6 also. So H6 is equal to HF plus X HFG. And now you just plug in all the value by using your thermodynamics table, and this value X you already find 0.9661, and then 2133.4 comes from your thermodynamics table. You can solve it and you will get the enthalpy value kilojoule per kg. For P7 you already know the pressure of 720 kilopascal. Okay, again it is a two-phase region, so you have to find the quality first by using the same approach we already discussed previously. S7 minus SF over SFG, which is equal to 6.7219, 0.8320, and in the denominator it will be 7.0752, and if you can calculate it, it turns to be 0.8325. Okay, so now 0.7 quality is also known to us. So H7 you can easily find using the same relation HFG against your 20 kilopascal data. Okay, so just plug in all the value and you will get 14.0 kilojoule per kg for your H7. Okay, so all the states are known to us now. Okay, so now another important thing, you have to find the Y. Okay, so we have to find Y. So again you have to apply energy balance equation. Okay, so we will just come from this one. Okay, so we have to apply energy balance equation of our closed field water heater. Okay, so if you can notice that this is coming in, this is coming in, this is going out, and this is going out. Okay, so then you have to just make it m2 m dot 2 h2 plus m dot 6 h6, because these are e in, is equal to m dot 3, this is going out, to h3 plus m dot 8 into h8. Okay, so this is your energy balance equation. So again, you already know that your m dot 8 is equal to m dot 2 is equal to 1 minus y, because we just assume that your y fraction is coming over there and 1 minus y is coming over there, and your m dot 6 is equal to m dot 2 is equal to y. Okay, so you just plug in the value in your equation, and you have to just solve it for your y, and you will find the y fraction easily. Okay, so we will just take a look over there. Okay, so by using the same relation, we get 1 minus y h8 minus h2 is equal to y h6 minus h3, and your y fraction will be h8 minus h2 or h6 minus h3 plus h8 minus h2, which is equal to, you have all the enthalpies value h8 h2 h6 h3 h8 h2, you already find all these values. Okay, so just plug in all the values and you will get the value 0.1463. So y fraction is known to us, so our main objective is to find your the W net and your thermal efficiency. So we need Q in first. So Q in is between H5 minus H4. Okay, so you just correlate with your your schematic diagram or TS diagram. So H5 is known to you, H4 is known to you. So you can just plug in these value. Okay, so kilojoule per kg, and Q out, again it is in the condenser part and fraction is going 1 minus y, so h7 minus h1, and 1 minus fraction you already know 0.1463, h7 is also known to you, so minus 251.42, and that turns to be 1675.4 kilojoule per kg. Okay, so W net you can easily find Q in minus Q out, and Q in is known to you, Q out is known to you, plug in the value and you will get 1016.8 kilojoule per kg. Okay, so now the only last step, which is your thermal efficiency. So thermal efficiency, we already know the formula of thermal efficiency. Thermal efficiency 1 minus Q out over Q in. So Q out is known to us 1675.4 and Q in is known to us also. Okay, so you just solve it and you will get 37.8% of your thermal efficiency. So this is how you have to solve your closed feed water heater problem. Okay, so if you have any question, you can ask me now. Okay, so there is no question. Okay, so this is now another example, which is example 10-6. Okay, so this is a very good example in order to understand the cumulative effect of your open feed water, closed feed water, and reheater also. Okay, so if you can just consider a steam power plant that operates on an ideal regenerative Rankine cycle with one open feed water heater, so one closed feed water heater, and one reheating process also. Steam enter the turbine at 15 megapascal. So your highest pressure temperature is given, is condensed in the condenser at a pressure. So 10 kilopascal is known to you. Some steam is extracted from the turbine at 4 megapascal for the closed feed water. So closed feed water heater, the extracted steam is at pressure, this one, and the remaining steam is reheated at the same pressure. So the pressure and the temperature is same for this one. The extracted steam is completely condensed in the heater and is pumped to 15 megapascal before it mixes with the feed water at the same pressure. Steam for the open feed water is extracted from the low pressure turbine. So another important thing is, because this is a reheating process, so one high pressure turbine is installed and one low pressure turbine is installed. So the steam that is going towards your open feed water heater is extracted from your low pressure turbine, and the steam that is going towards your closed feed water heater is extracted from your high pressure turbine. So the pressure is given also. So determine the fraction of the steam extracted from the turbine as well as the thermal efficiency of the cycle. So this is a very lengthy problem also. So what you have to do is, this is your home assignment, or you can just homework. You have to do it by yourself whenever you are free, but this is a very important one, so you have to understand it okay, well, because you can see this type of question in your sessional exams also. Okay, so you have to go through this. Okay, so now coming towards your okay, so this question you have to do it by yourself. Okay, so this is the same question we already solved okay, in this lecture, but the only difference is that previously the pressure is 20 kilopascal. Now we just have the pressure of 10 kilopascal, so it is changed. Okay, and it is not from your book, so you do not just have to copy from your book or any manual. Okay, so you have to solve it by yourself. What you have to do is, you have to just send me your ID and snapshot of your complete work. Okay, so you have to just snapshot and give the complete work. Okay, and you have to also draw the TS diagram. Okay, and send it to me. Okay, you will take 15 minutes or 15 to 20 minutes in order to do this work. Okay, so if you have any question, you can ask me now. It is a very simple question. There will be no difficulty if you understand the question well, which we already solved in this session.
सर कंप्लीट क्वेश्चन ही सर टेस्ट सॉल्व करके भेजें सर.
जी, कंप्लीट क्वेश्चन आपने सॉल्व करके उसकी पिक्चर आपने स्नैपशॉट लेके मुझे भेज देना, आपने इनबॉक्स करना. So you just have to note down the question, but after this screen will be disappear, so it will be difficult for you to find the question also. Okay, so I hope there will be no question over there. And also one student who asked me one question, Muhammad, I think Hassan Mustafa, or he's available now? Muhammad Hassan Mustafa.
Yes sir.
जी, आपने क्वेश्चन मुझसे जो किया था एक कि आपने मुझे सेंड किया था अपना सॉल्यूशन.
Yes sir.
तो उसमें आपको क्या इशू आ रहा था?
उसमें इश्यू तो नहीं है, बस सर ये था कि वो जो थर्ड पॉइंट था वो अंडर डोम आ रहा था, तो मैं ये बस कंफर्म करना चाहता था कि कैसा हो सकता है.
अच्छा, वो मैंने
उसकी
आपको इसलिए सॉल्व किया था, मैं आपको सोल्यूशन उसका एक दिखा देता हूँ, ठीक है। अच्छा, ये आपका सोल्यूशन है उसका, ठीक है। मैंने वैसे क्योंकि अभी रेफ्रिजरेंट 134A के क्वेश्चन आपको कराए नहीं है, तो उसके दो तरीके होते हैं। एक, या तो आप थर्मोडायनामिक टेबल से निकालें उसकी वैल्यूज एंथैल्पीज की, दूसरी आप पीएच डायग्राम जो हमारी A16 आई थिंक उससे निकाल सकते हैं। So initially you have to just start that you don't know that this point 3 is inside the dome or outside the dome. So you have to check it with your data. Okay. So in this lecture also we talk about that you have to check from entropy whether this point 3 is inside or outside. Okay. So all the things are I think you solve it correctly in your solution. So this is also right in your question also. So again, if we just come towards your point number 3. Okay, so for point number 3, you have to just check using this one. Okay, if you notice that SG, we have to just look for your P3 2 megapascal, and you can just find out that if this SG is greater than S, it will be two-phase region. So it's mean that if you are working on the two-phase region by using this condition, you are going in the right direction. Okay, so it is not like this that if you develop on a TS diagram that it is a superheated state, and then you come towards state number 3 and you find that it will be a two-phase region, that your TS diagram will be wrong. Okay, so it's mean you have judged from your data, available data, or not from your TS diagram completely. Okay, so again the efficiency will be 10.7 for this cycle. Okay, so there will be no difficulty in this, you can easily find it. Okay, so this is your solution for that question. Okay, clear?
yes sir, thank you sir.
Okay.
बेसिकली वो यही था ना कि सर रेफ्रिजरेंट में 2 जो P3 है वो 2 मेगापास्कल रेफ्रिजरेंट का है ही नहीं, मतलब वो डाटा टेबल अवेलेबल ही नहीं है।
हाँ, जब कोई डाटा
तो
अवेलेबल नहीं है ना, अब जब डाटा अवेलेबल नहीं है तो उसको हम पीएच डायग्राम में भी देख सकते हैं, ठीक है। वो A16 आपका टेबल है, डायग्राम है,
ठीक है,
लेकिन वो हम
यस
अभी
सर,
देखेंगे उसको किस तरह रीड कर सकते हैं जब हम रेफ्रिजरेटर्स का टॉपिक पढ़ेंगे, ठीक है।
यस ठीक है सर, थैंक यू सर।
ओके। Okay, so I am going to leave now. If you have any question, you can also inbox me. Okay, so I will try to give the answer as I am free. Okay, so now I am going to leave. So take care and Allah Hafiz, and do follow the SOPs of COVID. Okay.